You've hiked past it 100 times. That dark, heavy, boring-looking rock sitting in the cut bank while you kept your eyes locked on the white quartz because somebody told you 30 years ago that quartz is where the gold lives. And you came home with an empty vial again. Maybe a few flakes, maybe nothing but black sand and a sore back. I want you to hear this clearly because it matters. That is not bad luck, and it is not a lack of skill. You were taught to read the wrong signal. Quartz is a container. It is not the reason gold is there. The rocks that actually pull gold out of the Earth's plumbing and lock it down are darker, uglier, and almost always ignored by hobbyists. Gold isn't rare. Knowing how to read the ground is rare, so here's what I'm going to give you in the next 20 minutes. 7 rock types that carry more gold on this planet than quartz ever has. Exactly what each one looks like in your hand. The geologic reason it works, where in a drainage to look for it, the 5-second field test that kills the fool's gold problem forever, and what these finds have actually been worth in dollars and ounces. The last one on the list is the one almost nobody outside professional exploration geology talks about. And in California, it has sat on top of more gold than any quartz vein ever did. Stay with me for that one. Before we start, if a creek has ever sent you home with an empty vial, tell me in the comments how long you've been chasing your first real color, because I read those and I know you're not alone. Now, the foundation, because if you understand this one mechanism, the whole list makes sense and you'll never need to memorize anything again. Gold doesn't float around underground as little nuggets waiting to be dropped. Deep in the crust, where temperatures run somewhere between about 250 and 400 degrees Celsius, gold dissolves into hot water that's carrying sulfur. Chemists call it a bisulfide complex. In plain English, sulfur is the taxi and gold is the passenger. That hot fluid rides up through cracks and shear zones, and as long as it keeps its sulfur, it keeps its gold in solution. It can travel miles that way and never leave a speck behind. So, the question that actually matters, the question that separates people who find gold from people who wash gravel for 20 years, is not where did the fluid go? It's where did the fluid lose its sulfur? Because the instant that fluid loses sulfur, the taxi door opens and gold drops out. And there are only a few things that strip sulfur out of a hot fluid. Iron is the big one. When sulfur-rich water hits iron-rich rock, the iron grabs the sulfur and makes pyrite, and the gold it was carrying has nowhere left to go, so it plates out right there. Geologists call it sulfidation. Carbon is the second one. Organic carbon in dark, muddy rock chemically reduces the fluid and forces the gold to drop. Third is a hard pressure drop, where fluid boils and dumps its load. Notice what's not on that list? Silica. Quartz is the leftover. Quartz is the fluid's own exhaust, crystallizing in the open crack after the chemistry is already done. That's why you can break 100 pounds of pretty white quartz and find nothing, while a rusty black rock right next to it is loaded. So the whole game is finding the rocks that are chemically hungry for sulfur. Here they are. Number 1 is Greenstone. And here's the part that shocks most people. Something on the order of 1/3 of all the gold humans have ever pulled out of the ground came out of greenstone belts, and most weekend prospectors couldn't identify one if they tripped over it. Greenstone is an ocean floor basalt and volcanic rock, mostly Archean, meaning 2.5 billion years old and up. That's been cooked and squeezed until the original black basalt turned dull green. In your hand, it looks like a heavy, fine-grained dark rock with a soft greenish-gray cast, sometimes almost olive, sometimes gray-green like weathered army canvas. It's dense. It has no shine. It's often studded with tiny rusty pits where sulfide crystals weathered out. Why does it work? Because basalt is loaded with iron and magnesium. That's the whole point. When gold-bearing fluid runs through a shear zone in greenstone, the iron in the rock strips the sulfur, pyrite forms, and gold plates out along the walls of the structure and inside the altered rock for feet on either side. The proof is the Abitibi Greenstone Belt straddling Ontario and Quebec. which has produced well over 180 million ounces of gold. At today's prices, that's numbers with a lot of zeros. In the field, you look for greenstone where it's been chewed up, foliated, sheared, streaked with rusty carbonate and thin quartz stringers running along the fabric, not across it. That's your target. Now, the beginner's mistake, and this is the painful one. People find the quartz stringer in the greenstone, chip out the quartz, wash it, and get nothing. Because in these systems, the gold is very often in the dark, altered rock beside the vein, not in the milky quartz itself. You threw away the ore and kept the packaging. And if you're wondering how you're supposed to tell rusty gold-bearing rock from rusty worthless rock, that brings us straight to the next one. Because it's the single most productive rock type in American history. Number 2 is banded iron formation. If you've never heard of it, you're not alone, and that's exactly why it's still overlooked. Banded iron formation, BIF for short, is a sedimentary rock laid down in ancient oceans before the atmosphere had much oxygen. It looks like nothing else on Earth once you know it. Fine, tight, parallel bands, usually a dark steel gray to blue-black iron layer alternating with a red, cream, or gray silica layer, in stripes anywhere from paper-thin to an inch or two wide. It is heavy in the hand, noticeably heavier than granite of the same size, and the iron bands are often slightly magnetic. Run a magnet over a chip and watch it grab. Why does it hold gold? Go back to the mechanism. BIF is the most iron-rich rock on the planet. When a gold-sulfur fluid moves through a fold or fault in banded iron formation, the reaction is instant and total. The iron eats the sulfur and the gold has to drop. Nothing on Earth is chemically hungrier for that fluid. Here's your proof point, and it's American. The Homestake mine at Lead, South Dakota, in the northern Black Hills, was hosted in a folded, iron-rich formation. From 1876 until it closed in 2002, it produced roughly 40 million ounces of gold. 125 years of continuous production from one deposit. In the field, you're looking in the Black Hills, parts of the Lake Superior region, and older terrains in the Rockies and the desert Southwest. And you focus where those bands are crumpled, folded, and shot through with rusty seams. The noses of folds and the sheared limbs, because that's where fluid concentrates. The beginner's mistake here is dismissing the whole rock as just ironstone, and worse, seeing brassy specks in it and calling them fool's gold and walking away. Which brings up our villain for the day. Let's kill the pyrite problem right now because it has cost more prospectors more good ground than any other single thing. Pyrite is brassy, pale, and hard. Gold is deep buttery yellow and it's soft. 3 checks, 5 seconds total. First, shade it with your hand. Gold stays bright yellow in shadow. Pyrite and mica go dull and gray the moment the direct sunlight comes off them, because they're reflecting light, not glowing with color. Second, look at the shape. Pyrite grows in cubes and flat faces with sharp, straight edges. Gold has no crystal faces you'll ever see in a pan. It's rounded, hammered, dented, torn. Third, press it with the tip of a knife or a pin. Gold dents and smears like lead. Pyrite crumbles into black powder and mica flakes and peels. If you have a piece of unglazed porcelain, the back of a bathroom tile works. Drag it across. Gold leaves a yellow streak. Pyrite leaves a greenish-black streak. That's the whole test. But here's the part almost nobody tells you. Even when it is pyrite, don't walk away. Pyrite is the fingerprint of the exact chemical reaction that drops gold. In iron formation and greenstone, fine pyrite in a rusty zone is not an insult. It's an address. You just stop looking for the gold in the pyrite and start looking for it in the rock, around it, and in the gravel downhill. Quick pause here because this next part matters if you're serious about not getting skunked again. Everything I just walked you through, the sulfidation mechanism, the field tests, the way to read altered rock, plus dozens more tricks like it, is inside the Gold Prospector's Bible. 2026 edition. 50 field-tested tricks to stop getting skunked, written for people who actually walk creeks, not for a lab. And right now it comes with the 30-day skunk-proof roadmap completely free. A step-by-step 4-week plan to pick your ground, Test it smarter and find your first real color. Link in the description. QR code on your screen. This is the season you stop guessing where the gold is. Number 3 is conglomerate, and this one holds the single most staggering statistic in the history of gold. Conglomerate is simply an old riverbed or beach turned to stone, rounded pebbles and cobble cemented into a solid mass. In the hand, it looks like natural concrete. Pebbles anywhere from pea size to fist size, usually gray, white, or tan quartz pebbles, packed tight in a dark gray or greenish matrix. The pebbles are rounded and polished, because a river rounded them before the earth buried them. The critical detail is the matrix, the material between the pebbles. In gold-bearing conglomerate, that matrix is dark, often full of fine pyrite, sometimes with a black carbon film. Why does it work? 2 reasons stacked on top of each other. First, it's a fossil placer. Gold that was already concentrated by a river got buried and locked in place, sometimes billions of years ago. Second, that carbon and pyrite in the matrix chemically held the gold and even captured more from later fluids. The proof? The Witwatersrand Basin in South Africa, a conglomerate they call Banket because it looks like almond candy, has produced somewhere north of 1 to 5 billion ounces of gold, roughly 1/3 to 40% of every ounce ever mined by humanity, out of beds often only a few feet thick. Now bring that home. In California, the tertiary channels, those buried ancient rivers up in the Sierra above the modern canyons, are the same idea, and hydraulic miners tore whole mountains apart to get at them because the pay was in cemented gravel, not in quartz veins. In the field, you look for a bench of hard, rounded pebble rock standing above the modern creek, and you look at the very bottom contact of that bed where it sits on the old bedrock. That basal foot is where the gold is. The beginner's mistake is panning the loose modern gravel below the outcrop and never once looking up at the cliff that's been feeding it for 10,000 years. That's the pain right there. Working a creek for years while the actual source sits 40 feet over your head. And there's a rock that tells you the source is close, even when you can't see the vein at all. Number 4 is Gossan, and this is the flag that professional exploration crews chase from the air. A Gossan is the rusty, weathered cap that forms over a sulfide body. When pyrite and other sulfides sitting underground get exposed to air and rain, they rot, and the iron rusts in place and stays behind. What you get on the surface is a spongy, porous, rust-colored rock in shades of brick red, orange, mahogany brown, and yellow ochre. Sometimes it's honeycombed with little empty cells where crystals dissolved out. Geologists call that boxwork, and it's the tell. Pick it up. It's often lighter than it looks because it's full of holes and it stains your hands. Why does it matter so much? Because iron does not travel. When sulfides weather, copper leaches away, zinc leaches away, but iron and gold stay right where they were. So a Gossan is a stain marking the exact spot where a sulfide body, the very thing that formed when gold dropped out of solution, reached the surface. And here's the bonus. As sulfides rot, they can free the gold that was locked inside them, so the top of a Gossan is often richer than the fresh rock below. Nearly every great gold camp in the American West was found by somebody noticing a red-brown stain on a hillside. In the field, look for a rust-colored ridge or knob where the surrounding rock is gray or green. Look for red-orange soil where the rest of the slope is tan, and then walk directly downhill and pan the first drainage that heads on it. The beginner's mistake is assuming rusty rock is just weathered junk. Rust is the smoke. Follow the smoke. Now, everything so far has been about iron. The next one works on a completely different principle, and it's the reason the state of Nevada outproduces almost everywhere else in the country. Number 5 is Carbonaceous, calcareous siltstone, and black shale. I know that's a mouthful, so let's make it simple. Dirty, limey mud rock full of black carbon. In the hand, it's dark gray to sooty black, fine-grained, breaks into flat plates or slabs, sometimes leaves a gray smudge on your fingers, and where it's been altered, it goes bleached, punky, and crumbly with rusty orange seams running through it. Why does it work? 2 mechanisms at once. The carbon is a chemical reducer. It forces gold straight out of solution the moment the fluid touches it. and the calcite in the limey layers dissolves in acidic fluid, which opens up pore space and lets the fluid soak sideways through the whole rock body instead of staying in one narrow vein. That combination is why these deposits are enormous. The proof: the Carlin Trend in northern Nevada. Since it was recognized in the early 1960s, it has produced tens of millions of ounces, and the state of Nevada by itself accounts for roughly 3/4 of United States gold production. And here's the thing that should stop you cold. In Carlin-type ore, the gold particles are typically a few microns across, invisible, no color at all in the pan, sitting inside the crystal structure of arsenic-rich pyrite. Ore that runs a 1/4 ounce to the ton looks exactly like a gray rock. Nothing. In the field, this is where you have to be honest with yourself. You are not going to pan invisible gold. What you can do is recognize the setting because these systems bleed. Look for those bleached, rusty, decalcified zones along fault lines and Great Basin ranges, and pay attention to the coarse gold that later, shallower processes remobilized into the drainages below them. The beginner's mistake is standing on a world-class gold system, panning nothing, and concluding the district is barren. It isn't barren. It's just not visible with your eyes. Look, I'll be straight with you. Reading rocks like this took me years of getting it wrong, and I put everything I wish somebody had handed me on day one into one place. The Gold Prospector's Bible 2026 edition is 50 field-tested tricks organized across 5 chapters: reading ground, testing fast, working bedrock, cleanup, and where to legally go. It includes the printable 10-minute streamside checklist you can fold in a pocket, and the 30-day skunk-proof roadmap still comes free with it, though I honestly don't know how long that gift stays in the bundle. If you've been watching videos like this one thinking this could finally be your season, that's the move. Link in the description below, QR code on screen. Make this the year you find your first real color. Number 6 is schist, specifically chlorite and talc schist in shear zones. Schist is metamorphic rock that got squeezed until its minerals lined up into sheets, so it splits easily and it shimmers. Chlorite schist is dark green and greasy looking. Talc schist is pale gray green and soapy. You can scratch it with your fingernail, which almost no other rock allows. Why does it matter? Because a schist zone is a fossil fault. Soft, slippery minerals like chlorite and talc form where rock has been ground and sheared under heat and pressure, and shear zones are the plumbing that carried the gold fluid in the first place. Find the shear and you found the pipe. In the motherlode of California, the great mines followed a shear system for well over 100 miles, and that belt produced tens of millions of ounces. In the field, look for a stripe of soft, splitty, shiny rock where a creek cuts across the country rock, a place where the water carved a notch because the rock there is weak. Pan directly below that notch. The beginner's mistake is the shimmer. Mica in schist throws off gold-colored flashes in the pan and breaks a lot of hearts. Back to our villain. Mica flakes float. They flash only when the light hits at one angle. They go dull in shade, and they shatter under a pin. Gold sits flat on the bottom of the pan, holds its color in shadow, and dents. 5 seconds, every time. Before the last one, let me tell you a story that puts all of this in perspective. In 1989, in the desert of Sonora, Mexico, a farmer went out with an inexpensive metal detector, the kind you'd buy for a couple of $100, and got a signal in weathered desert ground. He dug up a single piece of gold shaped like a cowboy boot. It weighed about 389 troy ounces, roughly 26 pounds. He reportedly sold it for a small fraction of what it was worth, and it changed hands more than once before it went to heritage auctions in 2008, where the boot of Cortez sold for over $1 ton. $5 million. One rock, one afternoon. And here's the lesson that ties it back. That man wasn't a geologist. He didn't have a lab. What he had was a detector and ground that had a reason to hold gold. Weathered, iron-stained desert placer country sitting downhill from altered rock. He didn't outwork anybody. He outlocated them. The same is true of the Manuel brothers, Moses and Fred. who in 1876 staked a claim in the Black Hills on iron-rich rock and sold it the next year to George Hurst and his partners for $70,000. That claim became homestake and gave up around 40 million ounces over the next century and a quarter. Neither story is about luck. Both are about standing on the right rock. Which brings me to number 7, the one I promised you, and the one almost nobody outside exploration geology talks about. It's called Listwanite, and in California the field name for its signature mineral is mariposite. Here is what makes it extraordinary. It isn't a vein rock at all. It's serpentinite, old ocean mantle rock, that got flooded with carbon dioxide-rich gold-bearing fluid and chemically rebuilt from the inside out. In the hand, it is unmistakable once you've seen it. The background is buff, cream, or tan because the fluid turned the rock to carbonate, anchorite, and magnesite, and it weathers to that pale, chalky orange-tan color that stands out on a green hillside from a quarter-mile away. Scattered through that pale rock are brilliant apple green to emerald green flecks and streaks. That green is mariposite, a chromium-bearing mica, bright green speckles in a cream-colored, rusty, weathering rock. Nothing else looks like it. Why does it work? Because serpentinite is one of the most iron and magnesium-rich rocks on the planet, and when gold-sulfur fluid soaks into it, every mechanism we've discussed fires at once. The iron strips the sulfur and drops the gold. The carbon dioxide converts the rock to carbonate and makes it brittle so it fractures and lets in even more fluid. And the chromium released from the old mantle minerals dyes the new mica that unmistakable green. The rock is literally color-coded by the reaction that concentrated the gold. Here's your proof. The Mother Lode Belt of California runs along a major serpentinite-bearing fault system, and the historic mines from Mariposa, north through Sonora, Jamestown, Angels Camp, Jackson, and Grass Valley are strung along it. The mineral was named for Mariposa County. The Sierra Nevada gold rush counted on the order of 100 million ounces over its history, and the hard rock heart of it followed those altered ultramafic contacts. In the field, you're looking for the contact, the boundary where serpentinite meets slate, greenstone, or schist. Walk that contact. When you find pale, tan, chalky rock with green speckles and rusty boxwork seams, you are standing on the exact chemical trap that made the Mother Lode. Then look for quartz nearby, but understand its role now. The quartz is the receipt, not the reason. In a lot of these systems, the gold is in the altered carbonate rock and in the sulfide-rich seams as much as in the white vein. And now the beginner's mistake that costs the most. People find serpentinite, notice it's slick and green and full of talc, decide it's barren ultramafic junk, and leave. They walk right off the one rock type in California that best predicts where the big mines were. Meanwhile, the green flecks in that pale rock are not mica in the annoying sense, and they're not malachite. Try the villain checks. Mariposite won't peel like biotite flakes, and it stays green in shade. It's a signal, and it's been sitting in plain sight since 18. So let me ask you, which of these have you actually held in your hand before without knowing what it was? The rusty, honeycombed Gossan? The striped iron formation? The pale green flecked rock at a serpentine contact? Tell me in the comments, because I'd bet money that at least one of you has kicked over a piece of Listwanite and never gave it a second look. Here's where you are now compared to 25 minutes ago. You know that gold rides in hot water on sulfur, and that it drops when it hits iron or carbon, which means you can predict where it stops instead of hoping. You can identify greenstone, banded iron formation, gold-bearing conglomerate, Gossan, carbonaceous siltstone, sheared schist, and Listwanite in the field. By color and weight and texture, with nothing but your eyes, a magnet, a knife point, and a chip of unglazed porcelain. You know the 5-second test that ends the fool's gold argument for good. Shade it, shape it, press it. And you know the mistake that has kept honest, hardworking people skunked for decades. Chasing white quartz because it's easy to see, while the rocks that actually concentrated the gold sat right beside it, looking like nothing at all. Always check your local rules and get permission or stick to public land where prospecting is allowed before you start moving material. That part matters as much as the geology. If this changed how you'll look at a cut bank next weekend, go ahead and subscribe, because the next time you walk a riverbank, you really don't want to be the person who steps over a fortune and keeps walking. Next time out, I'm going to show you how to read black sand layers and bedrock cracks, on which layer is the false bottom that fools everybody, and which one is holding your gold. Until then, keep your eyes on the ugly rocks, trust the iron, follow the rust. Good luck out there, gold hunter.